With the release of FreeCAD 1.0, it's never been easier to get into parametric modeling for free. This tutorial video is aimed at beginners in 3D modeling or anyone looking for a great alternative to paid CAD software. By the end of this tutorial, you'll be able to model this bike hub and all the parts that make it up, complete the full assembly, and even create an exploded view of it. This piece is a great example of a complex part that you'll be able to model easily. And trust me, if this guy can model it, you'll have no trouble doing it too. Look, this guy's using a stick. The video is split into chapters, so you can directly jump to the parts that interest you, like the assembly at the end. You'll also find a link in the description where you can download the sketches we'll be using in this tutorial, as well as the step files if you just want to focus on the assembly part. You can download them for free on my Ko-Fi page, or feel free to leave a small donation if you'd like to help support the channel. Let's start the tutorial now. The first time you open FreeCAD, a setup window will appear, allowing you to choose your language, unit system, navigation style, and theme. I recommend keeping the default settings. On this page, you can choose a workbench to start with. Since our bike hub only requires modeling tools available in the Part Design workbench, we can click on the parametric part icon to begin our design. This takes us to the workspace. Before diving into the modeling process, we'll make a few UI adjustments to enhance the user experience. We close the report view by clicking the Close button and move the task panel to the right by holding down the left mouse button. If you're new to FreeCAD, it's important to know how to move your views around the object. To see the navigation shortcuts, hover your mouse over the mouse icon in the bottom right corner. This will display a diagram explaining the different view modes. You can experiment by changing the different settings to find the one that suits you best. As for me, I'll stick with the default CAD mode. We will start by modeling the central axle of the hub, which is a very simple part to create. We will use a revolution operation followed by a pocket, and we will finish with a symmetry. These are three common operations used in 3D modeling, and I will show you how to perform them. You'll see, it's very simple. I will place the part we are modeling in the bottom left corner of the screen, and you will also find the sketches we will be drawing in the video description. Before we begin, it's essential to understand what a revolution is, as we will be using this operation frequently throughout the tutorial. A revolution creates a solid by rotating a 2D sketch around a defined axis. This is commonly used to model symmetrical parts such as shafts, rings, and cylinders, which is perfect for our bike hub. So we will start by creating this sketch, which represents a quarter of our axle, and we will perform a revolution around the x-axis to obtain half of our axle. To create a sketch, click on the sketch icon in the toolbar. You will see three planes appear. You need to choose one to draw your sketch. Since we want to rotate around the x-axis, we should select the XZ plane. So left-click on it, you'll notice that the 3D view automatically adjusts to be perpendicular to the plane. This allows you to draw flat, just like on a sheet of paper. In the toolbar, you can find the different drawing tools represented in white with red points, as well as the constraint tools, which are entirely red. We will switch between them to create our sketch. We will start our sketch using the polyline tool, which allows us to draw multiple straight lines with the same tool. Click on the icon and start your sketch by snapping to the origin of the axes. Then draw a horizontal line along the red axis. Near your cursor, you should see the tool you are using, along with the different constraints being applied. In our case, coincidence and horizontality constraint are applied as indicated by the red icons near the sketch. Above, you can see the length of your line, giving you an idea of its size. In our case, we aim for a value close to 45 millimeters, but it's not crucial since we can adjust it later. Left-click to confirm the length, then continue drawing vertically for approximately 10 millimeters. Then draw horizontally for approximately 16 millimeters. Draw a 6 millimeter vertical line followed by a 6 millimeter horizontal line. Draw an 8 millimeter vertical line downward, then draw a horizontal line extending to the green axis. Close the sketch by connecting it back to the origin point. To stop using the polyline tool, you can either right-click or press Escape. We have sketched the general shape of our axle, but it is not fully constrained yet. Using the Dimension tool, we will constrain the sketch by assigning specific values to it, like 47.1 for the bottom horizontal line. Next, we will set the left vertical line to 8.5 millimeters, which corresponds to the radius of the bearing we will use. For the highest point of the sketch, we will set a vertical value of 12 millimeters. We also assign it a horizontal value of 32.3 millimeter. You will notice that the lines gradually turn green, indicating that the sketch is becoming fully constrained. For the topmost horizontal line, we set a value of 5 millimeters. And finally, we set a value of 7.5 millimeters for the last vertical line that connects to the origin. The sketch is entirely green, which means it is fully constrained. However, as you can see in the view of the part, there are fillets and chamfers to smooth the edges. We have the option to create them now. To do this, click on the Fillet tool in the top menu. With the tool selected, left-click on these 4 points in the sketch. This will create fillets at the intersections of the lines. The sketch is no longer constrained because we need to assign a value for the fillet radius. Select the Dimension tool and set a value of 3.5 millimeters for the rightmost fillet. You will notice that the sketch turns green again, indicating that the constraints are applied. Next, set a value of 0.5 millimeters for the fillet above. The 2 remaining fillets will have the same radius. Instead of applying a dimension to each one separately, we will make them equal. Right-click or press Escape to stop using the Dimension tool. Then select all 3 radii and click on the Equal icon in the top menu. The sketch should turn green, and the 3 arcs should now each have a radius of 0.5 millimeters. To finish the sketch, we will create a chamfer on the leftmost edge. This will make it easier to insert the bearing onto the axle. To do this, go to the Fillet menu, click on the black arrow to the right, and select Create Chamfer. Then left-click on the leftmost point. Right-click or press Escape to stop using the tool. Using the Dimension tool, set a value of 0.5 millimeters as the radius for the dashed arc. Now the sketch is complete. We have applied all the desired dimensions as well as the fillets and chamfer. We can exit it by clicking the Close icon in the top right corner. Now we are going to create the revolution, or as our Spanish friends would say, la revolución. Make sure the sketch is selected, indicated by its blue color, then click on the Revolution tool. FreeCAD automatically performs the revolution around the sketch's vertical axis, which is not what we need here. In the right menu, we need to change the axis setting to base x-axis. We get the desired result. To confirm the operation, click on the OK icon at the top. Congratulations, you have just completed your first revolution of many to come. But as you can see in the part's reference diagram below, we are not done yet. We still need to create the hole in the axle and apply the symmetry. Rotate the part so that the left face of the axle is facing you. We will create a sketch on this face. Left-click on it to select it, then click on the Sketch tool. As before, the view will automatically adjust to be perpendicular to the face. We will draw a circle to define the diameter of the hole in the axle. To do this, select the Circle tool from the top menu and left-click on the origin of the axes. This will ensure that the hole is perfectly centered. Then type 10 millimeters to set its diameter, which will automatically constrain the sketch. Next, right-click or press Escape to stop the tool. The sketch is fully constrained and green, which means we can exit it. To create the hole in the axle, make sure that Sketch 01 is selected, then click on the Pocket tool. In the right menu that opens, change the type to Through All instead of Dimension. This will ensure that the hole goes through the entire length of the axle. And click on OK to confirm. Now, we just need to create a symmetry to complete the part. Select the last operation in the tree view on the left, then click on the mirrored icon in the top menu. In the right panel that opens, select Transform Body and choose the YZ plane as the symmetry plane. As you can see in the updated view, the operation is successful. We can confirm it by clicking the OK button. We have completed the central axle of our hub. You can click on the black arrow on the left to collapse the part's tree view and rename it to axle by pressing F2. You can also hide the part by clicking on the eye icon next to the body. The first step has been smoothly and successfully completed. If you've made it this far in the tutorial and you're enjoying it, don't hesitate to subscribe to the channel and leave a like. It really helps a lot. Thanks for your support. Now we will move on to modeling the most important and complex part of the tutorial, the main hub shell. This part will be created using a revolution, multiple pockets, a subtractive pipe operation, a symmetry, and a polar array operation. It is the perfect example of a complex revolved part to model. Before starting the modeling, we need to create a new body. To do this, click on the blue body icon in the top menu. Using the F2 key, we will rename it to Hub Cage. Just like for the axle, we will start with a revolution, which means creating a sketch. Click on the sketch icon in the top menu. Select the XZ plane as the sketch plane. The goal is to recreate this sketch, which is more complex than the previous one. If you have trouble seeing the constraints or dimensions, you can find the sketch linked in the video description. To start, we will use the polyline tool to roughly outline the shape of the shell. Start the sketch from the origin and draw a horizontal line along the red axis. Next, draw a vertical line that will define the end of the shell. Then, draw an oblique line connecting to the area where the spoke holes will be positioned. Next, draw a vertical line, followed by a horizontal line, and then another vertical line to define the spoke hole placement. Then, draw another oblique line similar to the one you previously created. Next, draw a horizontal line, then create a sharp bump before connecting back to the vertical axis. Finally, close the sketch by connecting it back to the origin. To avoid any mistakes, make sure you have the same constraints applied to your sketch as I do. Next, we will use the Dimension tool to constrain our sketch. Select the Dimension tool from the top menu and set the large horizontal line to 39.6 millimeters. Next, set the vertical dimension of the large vertical line to 15 millimeters. This will correspond to the outer diameter of our bearing. Set a vertical height of 20 millimeters for the next point. Press the Escape key or right-click the mouse to exit the Dimension tool. The two extreme points must be at the same height. Instead of adding another vertical dimension, we will apply a horizontal constraint. Select the rightmost point and then the leftmost point. Then, click on the horizontal and vertical constraint tool. The rightmost point should have aligned to the same height as the leftmost point. We can reuse the Dimension tool to set a vertical value of 16.5 millimeters for the sharp bump. Then, set a horizontal dimension of 24 millimeters for the point after the sharp bump. Set a horizontal dimension of 10.7 millimeters from the vertical axis to the right point of the sharp bump. For the top of the sharp bump, set a horizontal dimension of 6.5 millimeters. Press the Escape key or right-click the mouse to exit the Dimension tool. Now we will make the two diagonal lines of the sharp bump equal. To do this, select them and click on the equal icon to apply the constraint. Next, we will align the bottom points of the sharp bump at the same height. To do this, select both points and apply a horizontal constraint by clicking on the icon. Using the Dimension tool, select the slope and then the horizontal line to set the angle to 137 degrees. Still using the Dimension tool, set a horizontal value of 34 millimeters for the highest point of the sketch. And set 4 millimeters for the thickness of the spoke hole area. We have two remaining heights to set, 19 millimeters for the oblique line and 25 millimeters for the spoke hole area. Just like with the axle sketch, we will now add the different fillets. To do this, we will use the Sketch Fillet tool from the top menu. Click on the fillet icon and left-click on the 5 points of the sharp bump and the oblique line. Using the Dimension tool, set a radius of 1 millimeters for one of the arcs. Next, select the 5 arcs and apply an equal constraint. As you can see, even after adding the constraints, the sketch is not fully constrained. We need to identify where it is still underdefined. It appears that the angle constraint disappeared during the fillet creation process. We can either recreate it or apply other constraints. We will choose the second option. So select both slopes on either side of the bump and apply an equal constraint. All right, so now using the Dimension tool, give a dimension of 9.5 millimeters between the vertical axis and the blue construction point of the first fillet. That should help lock things in place. The sketch should now be fully green again, but we still need to add 4 more fillets. So go ahead and click on the fillet icon in the top menu. Then, select the 4 points in the spoke mounting area by left-clicking on them. Right-click or press Escape to stop using the tool. Then grab the dimension tool and set a radius of 1.4 millimeters for the 2 upper fillets and 2 millimeters for the 2 lower ones. You can either set a dimension for one fillet and then apply an equal constraint to the other, or just use the dimension tool to define all the radii. Totally up to you. That was a pretty tricky sketch to pull off, but now it should be completely green, meaning everything is fully constrained. So you can just go ahead and left-click on the Close button at the top of the right menu, make sure that Sketch 002 is selected, then go ahead and click on the revolution icon. Just like with the axle revolution, this one isn't happening along the right axis. In the Axis tab, switch it to Base X-axis. The results should match, and the revolution should be successfully completed now. You can click OK in the right-hand menu to confirm the operation. Now we're going to create the cavity to hold the bearing, so select the outer face of the shell and click on the sketch icon to create a new sketch on this face. Using the circle tool, draw a circle at the origin point of the axes and set its diameter to 30 millimeters. Then click on the Close button to exit the sketch. With Sketch 03 selected, go ahead and click on the pocket icon in the top bar. We'll set the hole depth to 7.5 millimeters, which matches the thickness of the bearing we're using, plus a little extra clearance. Press Enter or click the OK button to confirm the operation. We're going to create the cavity on the other side of the shell to allow the axle to pass through and to reduce the hub's weight. To do this, rotate the shell to see the opposite face. Select it and click on the Create a Sketch icon in the top menu. Using the circle tool, draw a circle at the center of the 2 axes and set its diameter to 28 millimeters. And click on Close Sketch to exit the editing mode. Making sure that Sketch 004 is selected, click on the Pocket tool in the top menu. In the Type menu, change Dimension to Through All so that the hole goes through the entire hub. Then click OK to confirm the operation. You should now have the cavity that will hold the bearing along with a smaller hole that goes all the way through the hub. Before we create the symmetry to get the missing part, we're going to make a small relief cut on the central bump as shown in this diagram. As you can see, the relief isn't a simple shape, so we'll use an ellipse to create it. The first step is to create a datum plane at the center of the bump so that the relief cut is perfectly centered. The ellipse will be drawn on this plane. To create this datum plane, you need to select the face that will be at the center of the shell. Don't hesitate to zoom in on the object to make the selection easier. It can be a bit tricky. Once you've successfully selected it, click on the datum plane icon in the top menu. A transparent yellow plane appears on the screen. This is the datum plane, but we still need to move it to the center of the bump. In our case, we'll simply apply an offset of -13.95 millimeters along the z-axis, which is the axis perpendicular to the datum plane. You can then press Enter or click OK to confirm the plane's position. The yellow datum plane should now be positioned at the center of the bump. This will allow us to draw our ellipse exactly at this location. To do this, first select the datum plane, then click on the Create a Sketch icon. The view should automatically adjust to be perpendicular to the datum plane, allowing us to draw our ellipse flat. To find the ellipse tool, click on the small black arrow next to the circle tool, then choose the ellipse tool from the drop-down menu. This might seem a bit strange, but we're going to draw the ellipse slightly off-center from the axis to avoid automatic constraint creation. Why I said ellipse as if I were he who must not be named from Harry Potter. You know, that guy. Tell me in the comments what your Hogwarts house would be. Personally, I'd be a Hufflepuff. Back to our topic. To start, set a horizontal value of 16.4 millimeters, then assign an angle of 180 degrees for the axis. To switch between dimensions, just press Enter. Next, set a vertical value of 18.1 millimeters. Press Escape or right-click to stop using the tool. Then, select the center point of the ellipse along with the origin of the axes, and click on the Coincidence Constraint tool in the top menu, or press C on your keyboard. The ellipse should now be automatically centered on the hub. You can go ahead and click Close to exit the sketch. To create this recess, we're going to use a subtractive pipe operation. We already have the path, but we still need the profile. Before that, let's hide the datum plane by clicking on the eye icon next to it in the tree view. Next, we're going to create a new sketch, making sure that the datum plane is not selected. Then click on the Create Sketch icon. We'll base our circle on the ellipse we just created, so make sure to select the XY plane to do this. Now, we're going to project the ellipse's point onto our sketch. To do that, select the External Geometry tool from the top menu, then click on the ellipse's point. The point turns purple, which means we can now use it to constrain our sketch. You can right-click or press Escape to stop using the tool. Using the Circle tool, which is now hidden under the Ellipse tool, draw a circle with a diameter of 3 millimeters on the purple point. The sketch is now fully constrained and turns green. You can exit it by clicking the Close button. To perform the subtractive pipe operation, first select the profile sketch 006, then the path sketch 005. Be careful with the order, as it's crucial for the operation to work correctly. Next, click on the subtractive pipe icon in the top menu. If you've selected the objects in the correct order, you can click OK to execute the operation. If not, you can still adjust the order of the sketches in the right-hand menu. You should now have a non-uniform recess on the shell. We can now create the symmetry of the part. To do this, select the subtractive pipe operation in the tree view, then click on the mirrored icon. In the right menu, select Transform Body. The symmetry should apply correctly. Then click OK to confirm the operation. For this part, all that's left is to create the holes to accommodate the wheel spokes in their designated positions. So let's start by selecting the face where the holes will be created. Then click on the Create Sketch icon. Next, using the Circle tool, create a circle on the green axis with a diameter of 2.2 millimeters. Using the Dimension tool, set a vertical distance of 22.2 millimeters from the origin to the center of the circle. Then click on Close to exit the sketch. With Sketch 07 selected, click on the pocket icon to create a hole. In the right-hand menu, change the type to Up to Face and select the surface where the hole should end. Then click OK to confirm the operation. This hub is designed for a rim that can accommodate 36 spokes, so we need to create a polar array with 18 occurrences on this side of the hub. In the tree view, select Pocket 003, then click on the polar pattern icon. In the right menu, you'll see that the correct rotation axis is already selected. You just need to adjust the number of occurrences to 18. Press Enter or click OK to confirm the operation. You might notice that we didn't create the holes all the way through the hub to apply them on the other side. That's intentional because the holes need to be offset to fit properly on the rim. So we're going to repeat the same rotation, but shift the position of the circle. So select the face where we're going to draw the whole circle with an offset, and click on the Create Sketch icon. Reposition the view to be better centered. Using the Circle tool, draw a circle with a diameter of 2.2 millimeters to the left of the vertical axis. Since we have 36 holes, there needs to be a 10-degree offset between each hole. So using the Line tool, draw a line from the center of the circle to the origin of the axes. Using the Dimension tool, set the oblique line to a length of 22.2 millimeters. If you haven't done it yet, set the circle's diameter to 2.2 millimeters. And finally, set an angle of 10 degrees between the oblique line and the vertical axis. The last step is to convert the oblique line into a construction line by selecting it and clicking on the construction icon in the top menu. You can exit the sketch by clicking the Close button in the right menu. With Sketch 008 selected, click on the pocket icon in the top menu. Rotate the camera to see the exit of the hole. Change the type to Up to Face, select the back face and click OK or press Enter to confirm the operation. Next, select Pocket 04 in the tree view, then click on the polar pattern icon. Change the number of occurrences to 18, then click OK or press Enter to confirm the operation. We could have combined both pockets into a single polar pattern, but I didn't want to overcomplicate things and risk losing you along the way. I just want to say congrats on making it this far. Give yourself a high five because this was by far the most complex part to model in this tutorial. To top it all off, we're just going to add a small fillet to the recesses to make everything look a bit smoother. To do this, select the 4 edges of the recesses while holding down Control, then click on the fillet icon in the top menu or right panel. In the right menu, adjust the radius size to 0.3 millimeters. Press Enter or click the OK button to confirm the operation. This part is definitely finished now. We're going to move on to modeling the bearing cover that will sit against the shell. You can optionally make the axis visible to get a preview of your work so far. Modeling the bearing cover will be really simple. It'll mainly consist of a revolve operation followed by 2 pockets, nothing fancy but effective. To start, let's hide the axle and the shell by clicking on the eye icon. Now, click on the blue Create a Body icon. Using the F2 key, rename this new body to Cover Bearing to keep the file organized. Next, click on the Create a Sketch icon in the top menu and choose the XZ plane to draw your sketch. The goal is to recreate this sketch. The only particularity is that it has a small offset to the left, but otherwise it's nothing too complex. If it's easier for you to follow along, you can download the sketch from the link in the video description. To start, we will use the polyline tool, which can be found in the top toolbar, and we will draw a horizontal line starting from the origin followed by a vertical line. Then press Escape or right-click to stop using the tool. Restart the sketch from the origin, drawing a vertical line, then a horizontal one, followed by another vertical line, and finishing with a horizontal line. Right-click or press Escape to stop using the tool. With the Dimension tool, give a value of 10.9 millimeters for the large horizontal line and 10.9 millimeters for the vertical line on the left. For the first notch, give a value of 0.3 millimeters and 0.2 millimeters for the second notch at the top. Then give a vertical dimension of 15 millimeters for the topmost point of the sketch. Right-click or press Escape to stop using the tool, then click on the Create Arc by Center icon in the top menu. Left-click to place the center of the arc above the drawing, then left-click again on the rightmost endpoint of the sketch, followed by another left-click on the left side to complete the arc. Right-click or press Escape to stop using the tool. Select the point of the arc and the highest right point of the sketch, then click on the Coincidence tool to make them coincident. Next, use the Line tool to draw a line and make the arc tangent to this line. Select the arc and convert it into a construction line. Next, select the arc and the construction line, then apply a tangency constraint by clicking on the tangency constraint icon in the top menu. Next, select the right point of the arc and the right point of the offset, then click on the auto constraint for horizontality/verticality. To make things perfect, even though it's not mandatory, you can apply a length constraint to the construction line using the Dimension tool. The sketch is now complete and fully constrained. You can exit it by clicking the Close button in the right menu. We are going to perform a revolution operation. To do it correctly, make sure you have selected Sketch 009, then click on the revolution icon in the top menu. The revolution is not happening around the correct axis. In the axis attribute, change it to base x-axis, and click OK to confirm the operation. Now we will create the 2 pockets to allow space for the central axle. We will perform the first operation on the inner face of the part. So select the interface and click on the Create a Sketch icon in the top menu. Using the Circle tool, draw a circle centered on the origin of the axes with a diameter of 17 millimeters. Then click the Close button to exit the sketch. With the Sketch 010 selected, click on the pocket icon in the top menu. In the right menu, change the length to 8 millimeters, then press Enter or click OK to confirm the operation. Next, select the outer face of the part and click on the Create a Sketch icon. Using the Circle tool, draw a circle centered on the origin of the axes with a diameter of 10 millimeters. Then click on Close to exit the sketch. With the Sketch 011 selected, click on the pocket icon from the right menu or the top menu. In the right menu, change the type to Through All. and click on OK to confirm the operation. The bearing cover modeling is now complete. We will now take care of the bearings. The bearing reference is 69032RS. For standard parts that are supplied by third-party manufacturers, I recommend always using the 3D models provided by the manufacturer to avoid any construction errors. For bearings, I suggest searching for the models you need on the SKF or Koyo websites, as their CAD files are freely available for download. In our case, we are using a Koyo bearing with an external diameter of 30 millimeters, an internal diameter of 17 millimeters, and a thickness of 7 millimeters. 3D files are available in many formats. Unfortunately, not in FreeCAD format, but we can use the step extension, which is well supported by FreeCAD. We specifically choose the step AP203 format, and then we download it. Before importing, we will hide the cover bearing by clicking the eye icon, then click on File and select Import. Next, navigate to where you downloaded the file, select it, and then click on Open. In the next window that opens, you can leave the settings as they are, then click OK. The bearing should display correctly and be ready to use with the correct dimensions. You can check its hierarchy in the tree view to ensure everything is in order. For better clarity in our 3D model, we will rename the part to bearing using the F2 key. If you plan to use the file for production, I recommend keeping the original reference name. Oh, we've been working on the file for 30 minutes and still haven't saved it. It might be time to do so. So click on the disk icon in the top menu and save your file. Now we're going to take care of the bolts, and we're not cavemen, so we're going to use the Fasteners Workbench to get them. Only cavemen still model their own fasteners. To install the Fasteners Workbench, it's very easy. Just go to the Tools menu, then choose Add-on Manager. You can click OK in the window that opens. In the new window that opens, wait for all the extensions to load. Then, in the search bar, type Fasteners. Click on it, then click on Install in the top right corner. Wait a moment for the workbench to install, then restart FreeCAD. When you reopen FreeCAD, the new Fasteners Workbench should appear in the drop-down menu of Workbenches. Click on it to open the Fasteners Workbench. As you can see, this workbench offers a wide range of references for the most commonly used fasteners. In our case, we will generate spacers and bolts. We will start with the spacer, so select ISO 7289 and click on it. Well, you might think it's not very spectacular, but don't be fooled. By selecting it in the bottom left menu, you can modify its properties and adjust it to the size you want. In our case, the diameter of our bolts will be 10 millimeters, so we will modify the diameter and set it to M10. You may also notice that in the tree view, the name of the washer updates automatically based on the selected diameter, which, let's be honest, is pretty fantastic. Now let's generate the bolt. To do this, click on the ISO 4762 bolt icon in the top menu bar. Select the newly created bolt, then go to the properties in the left menu and change the diameter to M10. Also adjust the length and set it to 35 millimeters. Well, now that our two fasteners are created, there's only one piece left to model, the bolt cover. Just like the bearing cover, the modeling process will be quite similar. We'll use a revolution followed by a hole operation instead of two pockets. This will be a more elegant way to drill the piece. So, to do this, we need to go back to the Part Design Workbench and hide both the washer and the bolt by clicking on their respective eye icons. Next, we'll create a new body by clicking on the blue Create a New Body icon. Using the F2 key, we'll rename it to Cover Bolt. Next, we'll click on the Create a Sketch icon and select the XZ plane as the sketch plane. The goal is to recreate this sketch, which is similar to the bolt cover, but simpler. We will start with the polyline tool and draw, starting from the origin, a horizontal line followed by a vertical line. Right-click or press Escape to stop using the tool, then start a vertical line from the origin. And draw a small horizontal line. Then, using the Circle Arc tool, draw an arc with its center on the top left side and a radius extending to the top right point. Press Escape or right-click to stop using the tool. Then, select the point of the arc and the point of the vertical line and click on the Coincidence Constraint tool. Use the Dimension tool to assign the following values: 11.5 millimeters for the horizontal line, 9.25 millimeters for the left vertical line, 10 millimeters for the right vertical line, 1.3 millimeters for the small horizontal line, and 20 millimeters as the radius for the arc. The sketch should now be fully green and fully defined. Click the Close button in the right menu. To perform the revolution, make sure Sketch 0112 is selected, then click the revolution icon in the top menu. Change the axis of revolution by setting it to the base x-axis, then press Enter or click OK to confirm the operation. To create the holes for the bolt, we will use a hole operation. We will select the left face and then click on the Create a Sketch icon. Using the Circle tool, draw a circle with its center at the origin of the axes and a diameter of 10 millimeters. Then close the sketch by clicking the Close button. Make sure that Sketch 013 is selected, then click on the hole icon in the top menu. In the right-hand menu that opens, change the hole cut type to counterbore. Set the diameter to 14.5 millimeters and the depth to 10.3 millimeters. You can rotate the part to view the result. It is the opening for the bolt head. Then, in the top part of the menu, change the diameter to 10 millimeters and the depth to through all. 2 holes should be created, one for the bolt shaft and one for the bolt head. Once everything is set correctly, click the OK button to confirm. To make the part more attractive, we will add a fillet. To do this, select the left edge, then click on the Fillet tool in the top menu. In the radius field, enter a value of 0.5 millimeters, then press Enter or click OK to confirm the operation. Congratulations, you've completed the modeling part of the tutorial. I think the revolution operation should hold no secrets for you now. Well done. We can now move on to the assembly. But before that, you can hide the last part by clicking on the eye icon next to the part in the tree view. We will group all the parts into the same group to clearly differentiate the parts from the assembly. To do this, click on the Create a Group icon in the top toolbar. With the F2 key, rename the folder to Parts. Then select all the parts and drag and drop them into the new folder. The goal now is to assemble all the parts we just created to complete this assembly. For the bad guys who are starting the video now and haven't modeled the parts, you can find the Step 3D files for all the parts in the video description. You'll just need to import them like we did for the bearing. You can hide all the parts by clicking on the eye icon next to the Parts folder. To create the assembly, we will use the Assembly Workbench, newly introduced in FreeCAD version 1.0. It is perfect for this task and well suited for this type of assembly. Go to the Workbench drop-down menu and select Assembly. To create an assembly, you first need to click on the Create Assembly icon in the top menu bar. In the tree view, you'll see a new object called Assembly with a folder named Joints. All the imported parts will be stored in this assembly object, and the different types of joints between the parts will be stored in the Joints folder. You can rename the assembly to Complete Hub using the F2 key to keep the file organized. The first step in an assembly is to import the parts that will be part of the assembly. In our case, all the parts have been created in this file, but you can easily import parts from other files as well. To import parts, simply click on the Insert Components icon. A menu opens on the right asking which objects you want to import. As you can see, you can import all types of objects such as part design bodies or even sketches, which can be very useful for constraining an assembly. In our case, we will only import the parts we created and constrain them together. To start, we will insert the central axle of the hub, which will be fixed and will not move. To insert it, click on it in the menu on the right. A pop-up window appears asking if you want the part to be fixed. Grounded. You must have at least one part that does not move. In our case, the central axle is considered fixed, so we can click Yes. We also have a gizmo that allows us to move the part if needed. Since we want the axle to remain centered, we don't touch it. You can then insert the hub cage by clicking on it. Here you can use the gizmo to move it and prevent it from interfering with the axle. Then click on the bearing and use the gizmo to move it to the right. Repeat the same operation, but this time move it to the left. Insert a cover bearing and move it to the right. Repeat the same operation, but this time move it to the left. Insert a washer and move it to the right. Repeat the same operation, but this time move it to the left. Insert an M10 bolt and move it to the right. Repeat the same operation, but this time move it to the left. Finally, insert a cover bolt and move it to the right. Repeat the same operation, but this time move it to the left. We've now finished inserting all the parts, even though it feels like DJ Casper's cha-cha slide with all those rights and lefts. Click OK to close the right menu and stop importing parts. Everything seems a bit disorganized, but it will come together. Just a bit of patience. We will start by constraining the hub shell onto the axle. This will be very simple. We will apply a revolute joint. This type of joint allows us to position the part at the center while giving it the freedom to rotate, just like in real life. To do this, since both the shell and the axle are cylindrical, simply select the central face of the shell, then the central face of the axle while holding down Control, and then click on the Create a Revolute Joint icon. The shell should now move directly to the center of the axle in the correct position. They should share the same axis of revolution. In the right menu, you have the option to make adjustments, such as applying an offset or setting minimum and maximum rotation limits. In our case, we want the shell to rotate around the axle by 360 degrees. So we can leave the default settings and click the OK button. We can test the rotation of the shell around the axle by holding down the shell and rotating it. We can see that the part only moves in rotation, which is exactly what we wanted. Now we can move on to the other parts, starting with the bearings. For this joint, the bearing is pressed into the shell, which means the bearing will be fixed within the shell. This type of joint prevents any movement or rotation of the part, which is perfect for our case. To create this type of joint, select an edge on the face that will be in contact with the shell, and then select the corresponding edge on the shell while holding Control. It might be tricky to select, so don't hesitate to rotate the object to get better access. Then click on the Create a Fixed Joint icon in the top menu bar. The bearing should position itself perfectly in its place and be fixed to the shell. We can leave the default settings and click the OK button to confirm. Now let's repeat the same operation for the right bearing. Select an edge on the left face of the bearing, then select the corresponding edge on the shell, just like you did for the other bearing. And do all of this while holding the Control key. Then click on the Create a Fixed Joint icon in the top menu bar. If the bearing is correctly placed, you can click OK to confirm the operation. Now we will repeat the same operation for the bearing covers. We will select the edge of the cover, but the one located after the extremity so that the small section fits inside the hub shell. It's the edge indicated by the red arrow, which you need to select by left-clicking on it. While holding Control, select the corresponding part of the shell, specifically its outer edge. Click on the Create a Fixed Joint icon. You can also use the revolute joint. For our demonstration, it doesn't make a big difference. The cover should now be in the correct position. You can click OK to confirm. We will repeat the same operation for the left cover bearing. Select the edge with the largest diameter on the far right. While holding Control, select the outermost edge of the shell. Then click on the Create a Fixed Joint icon in the top menu toolbar. Again, you can choose to create a revolute joint, which is technically more accurate. As you can see, the piece hasn't positioned correctly. To fix this, you need to flip it. To do this, click on the icon with the two arrows in the right-hand menu. The part should now be positioned correctly. You can click OK to confirm the operation. You now have all the tools to position the remaining 6 parts. For each one, simply select the 2 outer edges that will be in contact and apply a fixed joint. I'll speed up the video by 3x, but if you want to follow along at real-time speed, you can adjust the playback speed by clicking on the gear icon. And we'll meet at the end to create an exploded view of the hub. Congratulations, you have now completed the assembly of the hub. Before we start the exploded view of the hub, let's clean up the tree view a bit by clicking on the black arrows next to each part so that only the part names are visible. This will make the tree view less overwhelming. Next, click on the eye icon next to the joints line to hide the locked parts in the viewport. To create an exploded view, it's very simple. Just click on the Create Exploded View icon in the top menu bar. Next, you need to select all the parts you want to show in the exploded view from the tree view. All the parts of the hub should turn blue in the viewport. Then click on Explode Radially in the menu on the right. Using the gizmo, move the pieces along the red axis to create the radial exploded view. You can switch to the top view for a better overview of your exploded assembly using the view cube in the top right corner of the screen. You can move each piece individually by selecting them in the viewport and using their dedicated gizmo to place them wherever you want in space. For my part, I move the bolts so they are more detached from the assembly, and I also subtly move the bearings so they are less attached to the other pieces. Once you're happy with your exploded view, you can click OK in the right menu to confirm. As soon as you click OK, the assembly will return to its original position. To access the exploded view again, you need to click on the exploded view line in the tree view. You have the option to modify your exploded view again at this point. Great. Now that you're happy with the exploded view, you can click OK to confirm it. To add more realism, you can make the threads of the bolts visible. To do this, go to the Parts folder, click on the M10 bolt, and in the Data Properties menu at the bottom left, change the thread setting to True. Note that this may slow down your computer, as generating the threads consumes quite a bit of processing power. To minimize the slowdown, you can go to the View properties and change the deviation to a higher value, like 10. This will make FreeCAD simplify the display, improving performance. When you return to the exploded view, you should see the threads of the bolts displayed. You should know that you can use this exploded view to create a technical drawing. If you're interested in that, you can find my tutorial on it in the description. This marks the end of this tutorial. If you're interested, you can purchase the FreeCAD file from this tutorial. You'll find the link in the description. I hope this tutorial has helped you better understand how FreeCAD works and how to create an assembly with it. If not, I hope it still entertained you. Let me know in the comments what topics you'd like to see covered in future videos. Thank you for your attention.